Hello and welcome to Scientific Computing's webinar on deep learning. I'm Tim Stutt with Scientific Computing and I'll be your moderator for today's webinar titled Accelerate Your Big Data Strategy with Deep Learning. This webinar is co-sponsored by Dell EMC and NVIDIA. We thank Dell and NVIDIA for their support in making this instructional session available free and on demand to our audience. Today's business models have big data at their core, and as the amount of data being generated increases exponentially, the ability to extract insights and knowledge becomes even more critical. This is where artificial intelligence, or AI, is leading the next wave in industry transformations. In today's webinar, our speakers will tell you how organizations can accelerate their data strategies with deep learning techniques, the fastest growing field in AI. They'll also tell you that by using data-driven algorithms powered by GPU accelerators, your organizations can get faster insights. We hope that today's webinar will give you a feel for the technologies and challenges of these research efforts and some of the solutions that are being implemented. Today's one-hour webinar is offered free to our audience and will be available online on the Scientific Computing website following the live session. Following our speaker presentations, we'll have a short Q&A session. The audience can ask specific questions in the email box provided on your screen, and we'll try to get to as many of the questions as we can. All unanswered questions will be forwarded to the speakers for their one-on-one responses. Please send in your questions anytime during the presentation. Today's speakers include Paul Teich, who is Partner and Principal Analyst at TIRIAS Research, and Will Ramey, who is a Senior Product Manager in GPU Computing at NVIDIA. Paul Teich has more than 30 years of industry experience in computing, storage, and networking. His strength is in assessing the technical feasibility and market opportunity for new technologies and developing profitable strategies to commercialize those technologies. Paul's prior experience includes being a key member of AMD's Opteron server processor team in the early 2000s, which redefined 64-bit computing. He also was a product manager of RISC processors, which were used as graphic accelerators in the early 90s. These are now popular again for deep learning applications. Paul currently works on the future of computing from the sensor to the cloud and the resulting changes in technology, industry, and society. Will Remy is NVIDIA's Director of Developer Marketing. Prior to joining NVIDIA in 2003, he managed an independent game studio and developed advanced technologies for the entertainment industry as a product manager and software engineer. He has a BA in computer science from Willamette University and completed the Japan Studies program at Tokyo International University. And so now, without further ado, let's start our webinar with Paul Teich, and please don't forget to send in your questions for the Q&A session.
Thanks, Tim. Much appreciated. So we talk about artificial intelligence, AI, all the time, but what do we mean when we say it? The end game is that AI, true AI, is going to be equivalent to human intelligence. It's going to demonstrate independent thinking and reasoning, and we're not there yet, not for a long while. Until we get there, we use AI as an umbrella term for a set of technologies that borrows from our current knowledge of how biological systems perceive their environment and how they learn from it. So it's important to remember that we're still at an early stage of development of AI. About a year ago, Andrew Ng of Baidu said, "We're drawing stick figure cartoons of how we think the human brain might work." However, in the short term, those stick figures turned out to be pretty useful. So machine learning systems are demonstrating an ability to learn from data today. And cognitive computing systems are starting to show some situation environmental awareness. But how are they different than our current generation of data analytics? So machine learning is dependent on deep learning techniques. Deep learning is based on neural networks. Neural networks enable what we call reinforced learning. They learn from feedback. When you create a neural network model and then keep feeding it data, it refines what it learns and it even adapts over time as its input data changes. So in essence, it can learn what a new normal is for a system as a system evolves. So when you create a neural network model and then keep feeding it data, it basically changes on the fly. Deep learning is based on multiple layers of neural networks, from a handful of layers to hundreds of layers in modern state-of-the-art applications, emerging applications like autonomous driving and natural language processing. Today we're at a stage where humans oversee the structure of the neural network models that we're building. So people help deep learning systems adjust to incoming data when they get stuck in a close but not optimal solution. We call this supervised learning. The majority of deep learning models today are supervised learning. The ultimate goal of deep learning, though, is unsupervised learning, where the algorithms can find optimal solutions with no human intervention. We're not quite there yet. Obviously, it's gathering a lot of research investment right now, but unsupervised learning will enable the next true steps in AI evolution. In the meanwhile, we associate AI and machine learning and deep learning with high-performance computing today. These technologies and techniques were all over the supercomputing SC16 conference last week. And most of us are aware that cloud services are powering up machine learning systems. AWS, Google, Microsoft, Baidu, you name a major cloud service and they're running deep learning in their cloud for their own use. And they're also exposing tools for customers to take advantage of deep learning. What's not so obvious is that deep learning is also being used today for malware detection within service and data center networks. So the old IT approach was to put up a firewall of security. And from a hacker perspective, as we're seeing today in a number of situations, it's kind of like a polar bear looking at an igloo. It's hard and crunchy on the outside, but soft and chewy on the inside. All you have to do is get through the firewall, and you're kind of unimpeded inside a large system. Today's advanced threat detection security measures look at the behavior of systems attached to a network, and deep learning is becoming a powerful tool to look for exceptions to normal behavior. So once you've implemented deep learning in your network behind the firewall, deep learning can be used for many other tasks, not just advanced threat detection. Eventually, deep learning is going to migrate to the edge of the network into all of the devices that we use in our lives, from smartphones to buildings. This will happen because networks and services take time and power to access. And some decisions need to be made on a local basis as fast as possible while using as little power as possible. So there'll be trade-offs where machine learning takes place, from local devices to cloud-based services. There'll be a big difference in how deep learning is implemented also from data center to endpoints, in that bigger systems are needed to train deep learning models. You need to crunch through a tremendous amount of data to generate a useful model and to keep it updated over time. Smaller systems can be performance and power tuned to run models fast and efficiently. And we have a few names. The industry hasn't really settled on a name for this whole running a model thing. There's inference, classification, recognition, implementation, etc. And for this presentation, Will and I will use the word inference for running a model that's already been trained to recognize patterns in real-time incoming data. So the big question is, why now? We've been working on neural networks for decades, and you've probably all heard the adage up until the last year or so that speech recognition is always 5 years away. It's been 5 years away for 30 years. But something changed. And what happened was that multi-layer neural networks were developed about 5 years ago. And there was a confluence of other technology that hit at about the same time that kicked off this recent explosion. Some call it the Cambrian explosion, modeling biology a few 100 million years ago, of machine learning. So the pre-existing conditions were, first and foremost, that deep learning needs massive amounts of data for even the basic supervised model development. So where do we get that data? We look at places like network traffic as the World Wide Web continues to connect global e-commerce, and the growth of social media, and the growth of the Internet of Things. On a smaller scale, instrumenting your business from managing your IT infrastructure excuse me, to your supply chain, to customer preferences and satisfaction also generate a large amount of data in real time. If anyone tells you only gather the data you know you'll need, then I think they don't understand the value of machine learning generated insight. So part of the equation is to both software and hardware instrument your business. Put sensors in software, put sensors in hardware, and gather as much data as you economically can afford to gather, because that will give you the true insight out of the deep learning process. The whole point of implementing machine learning is to sift through volumes of data that would take humans lifetimes to simply read. And then it pulls out nuggets of insight that create competitive advantage and perhaps even in the process move society forward. Secondly, we need to be able to process these new neural network algorithms and all of this data in useful time frames. This is where the GPU acceleration part comes in handy. To NVIDIA's credit, they saw the promise of leaning in and funding machine learning products and tools and the development of this whole ecosystem early in the deep learning cycle. Scale-out computing also matters hugely to the cloud giants. And that's where the server and data center infrastructure and Dell EMC come into the picture. They matter in that scaling out deep learning resources to support training, to support the inference that you build the services on that are customer-facing, such as like Amazon's Alexa, aren't possible without scale-out data center infrastructure. So if you have a business model, then you can use machine learning to improve your performance. The big difference between machine learning and big data is that big data requires people who understand statistics, so data scientists. Supervised machine learning requires people who are trained to use model development tools. So there's a qualitative difference in the kind of people that you're looking for to go implement deep learning, machine learning, and artificial intelligence. Frankly, as deep learning is getting a lot more attention from university and training perspective than data science has, because one is procedural and hip, and the other requires learning statistics, really learning it. And I think the models and procedure will win every time. And it's kind of why we graduate more programmers from universities and training programs than actual computer scientists. So as I said, unsupervised learning will be able to develop insight by itself. And even when we get there, you'll still need database administrators or their equivalent, because this is based on these high volumes of data. Data hygiene, data normalization are critical first steps in developing deep learning models. So today, the big machine learning and cloud applications are in image recognition and natural language processing. The short steps are toward behavioral analysis and sentiment analysis. And so while some gadgets promise that they're based on neural networks or machine learning, the reality is that training happens in a data center or on a dedicated server-like appliance for at least the next few years. Training, both for cloud services, for networks and devices, will also depend on GPU technology for the next few years, both for power efficiency and for speed. We'll see a lot of investment going into developing new chip architectures also, mostly to accelerate inference. And the goal here is to lower the cost of an inference transaction so that services can scale better, and so that low-power devices can become better at inferencing while chewing through less battery power. But these new architectures are also probably a few years away. There are many of them that are diverse, and they're in a very embryonic state right now. The next challenge is that new deep learning techniques and frameworks are developed on almost a weekly basis. You read about Baidu and Tencent and Google and Amazon developing these new classes of models and algorithms and kind of throwing them over the wall. It's really hard to predict when this is going to slow down. It is a fundamentally new area of computer science research. One thing that I find absolutely fascinating is that medical research into the biological roots of human cognition is now being funded by those cloud giants. Think about that for a second, because pharmaceutical companies usually and typically fund this kind of medical research. So we're just starting down the path of funding research into human cognition from the tech industry. And over the next few years, I expect that we'll see some rapid discovery of how humans think and why we think like we do. And that'll become the basis for developing new cognition models and deep learning techniques. So far from being at the end of the road, we're at the beginning of this one. So if we'd asked in 1945, what's the potential for business use of computers? I think the answer from almost any company you asked would have been, we have a bunch of them downstairs. They're people. They're people who are good at math, good at arithmetic. They used adding machines for accounting. They used slide rules for more advanced math. But we had bunches of them. It was a career path. That all changed as we implemented the first computing systems, as the PC came into the market, and created a fundamentally different work environment that doesn't rely on arithmetic skills anymore. So our math on predicting the value of implementing deep learning, machine learning, and AI is still a bit fuzzy at this point. Think of it like that IT productivity paradox. If you implemented IT and brought in PCs, you remained competitive, but if you did not, you weren't. So implementing new IT didn't boost competitiveness per se, but it did set the low bar for being able to compete at all in the market. And so if we look at the enabling technologies all coming into place, the memory, the storage systems, the wireless interface for mobile services, the neural networks, the ability to harvest energy at the end device to generate the data, we see that all feeds into a market that we've heard about augmented reality. It's probably the most, few people mention that augmented reality is a killer Internet of Things app, but it also requires that the system understand what the human is doing in real time to provide useful information, contextual information, as you're walking around repairing equipment or walking down the street or whatever you're doing, playing a game with augmented reality. Natural language processing. Every online service, every shopping service, e-commerce site is implementing natural language processing to better understand the needs of shoppers. And we look at the rest of it. The event prediction is kind of the old business intelligence question of when do we get to a point where we need to produce something or stop producing something. Security and autonomous vehicles are probably the hottest topics right now, in that they really, modern advanced threat detection and navigating real-life scenery are both not really possible to the quality we need without new deep learning techniques. So the potential for AI and machine learning is to commoditize repetitive cognitive tasks that use large amounts of data. It's a general purpose tool. It's akin to the spreadsheet, and it's going to be at least as transformative. So we've listed a few sample applications here, but if we take a deep dive into a couple, we'll find the rabbit hole is really deep. For instance, building automation. We talk about resource management and autonomous control. These are the building kind of operating itself. If you think about people going to work from 8 to 9 a.m. in the morning. If it's summer in Dallas, they're bringing a lot of heat into the building with them. If it's winter in Chicago, the building needs to be heated up and already warm for them by the time they walk in, because they're going to kind of bring in some cold air as those doors stay open for about an hour, hour and a half. And so planning usage patterns, also having individual rooms in a building customize themselves for the people who are actually at desks in the room or operating equipment in the room. So our infrastructure will become a lot smarter and more responsive to our needs. On the consumer side, I think most of the effort now is in understanding consumer behavior, and that focus will shift toward reacting to how people behave in real time. And I'm sure we've all gone shopping for something on Amazon, if you're in the U.S., and all of a sudden ads for that item start to pop up in completely unrelated websites. And if you were just curious, or if you actually bought it that first time you visit, you're going to see about 15 more ads for it before the system realizes that you're not responding to something that you've already purchased. You don't need a second one right away. This behavior will become a lot more intelligent and predictive If you bought this, then here's something else you'd like to see that's related to it, kind of analysis. For health and medical, I think that's also a huge promising area. And then it's not just about patient monitoring. It's about prescriptive regimens ahead of the need. So if you think about wearing an IoT device like a heart rate wearable, a step tracking heart rate wearable, that feeds into a system that will be able to determine your overall health as you simply walk and sit through life. And if you're an office worker, sitting is something we do a lot. Those predictive prescriptions will feed into a healthcare system that at some point might actually give users a lower rate to wear an IoT device to generate the data that will give us the pattern analytics to go use deep learning on to figure out when people are going to have a life-threatening event. So I think we could go on forever on this slide, but for your business, for your area of research, this is like the spreadsheet. This is a fundamentally useful tool for examining your competitive environment. So what does AI mean for the future? The opportunity is, I don't think this is actually something fundamentally new from the rest of IT for the last 50 years. I think this is continuing the trend of where IT has always been going on the grand cycle of industrial revolution, which took hundreds of years. We're just not very far into this IT revolution. So for me, this is a continuation of 50 years of semiconductor and systems evolution. The societal inflection point for artificial intelligence and machine learning and deep learning is going to be much like the PC, the internet, mobility. It's changing the way we work, changing the kinds of things we do, and even giving us new things to do, new ways of doing it. So AI can be combined with other technologies, all of the mechanical and physical systems around us, but even more than that, it actually can aid in interhuman interactions. So if you think about going to a website, Chinese website, a French website, for those of us who are American, Spanish, German, Russian. I've done all of that and hit the translate button, and in the last 6 months, the translations have gotten hugely better. So it's actually kind of intermediating between human relations on a very large scale. So AI is a symbiotic relationship between humans and machines that actually can aid human interaction. And so I think we see that this is only the beginning. The potential here is truly boundless. So with that, I'll hand it over to Will.
Great. Thanks, Paul. As you heard from Paul, deep learning is a new approach. It's a new way of thinking for almost everyone. So I'd like to take a few minutes to share with you the basics of why deep learning is so powerful and how it works, the challenges many organizations face when getting started with deep learning, and then also a little bit about GPU-accelerated software, training, and the end-to-end platforms that are available to help you address these challenges. Let's start by looking at an example of how this new computing model is different from the traditional approach. Consider the traditional approach of performing a task such as vehicle classification. This is where you have lots of pictures of different types of vehicles as they drive down the road from different angles, etc. And you need to be able to either count them or distinguish the difference between all of the different types of vehicles on the road. To accomplish this, you would have a domain expert, typically someone trained in computer vision, come up with a set of rules to extract the features from each image, things such as edges or corners or color information, etc. The expert has to then write a computer program to capture all of the rules that identify these specific characteristics. And these individual rules are sometimes called classifiers or feature extractors. They're trying to understand these little ingredients of each image that help you determine what it's a picture of. And as you can imagine, this can be really tedious and a very error-prone task. And if the data changes, say a new model of car is introduced each year, then you may have to go back to the drawing board. And all of this work results in tons of software code to write, debug, and maintain. The deep learning approach, in contrast, is to learn such capabilities directly from the data. So you would provide a deep learning framework, which we'll look at in more detail in a moment, with lots of example images to teach the neural network how to perform this task. This step is often referred to as training a neural network, and we'll talk about that in a little bit. The advantage of this approach is reduced reliance on the domain experts, because you don't have to manually write all of these classifiers or feature extractors. Deep learning can also easily adapt to new types of vehicles or other examples, simply by retraining the network with more different examples. And the whole thing benefits from an immense speedup using NVIDIA's GPU accelerators. And here you can see the example of that separate approach, that second approach using deep neural networks, where you can learn from the data and easily extend its capabilities simply by showing it new examples. So let's take a look just for a moment at how all of this actually works. You would first start with an untrained neural network. This is a network that has the capability to perform a specific task, but hasn't been trained with a specific set of data yet. So for example, this neural network might represent the design or topology of a neural network that is really good at image classification, the same example that we used on the previous slide of distinguishing between different types of vehicles. That same task would be good at distinguishing between different types of animals or different types of trees or even different species of dog. But it probably wouldn't be very good at speech recognition. You'd want to use a different shape of network. It might have more layers, it might have more or fewer connections between each of the little nodes or perceptrons in the layers, and so forth. But for this example, let's start with this untrained neural network, and here we see a kind of a simplified version of what we're going to use as an image classification network. The next step is to collect your training data or your training data set. And so if we are trying to train an image classification model, a neural network model, to distinguish between cats and dogs, we would accumulate a set of data that had thousands of pictures of cats and dogs, looking at them from all sorts of different angles and all sorts of different lighting situations and environments as examples. And for that training data set, we would actually know the label of each of those pictures. We would know whether it was a cat or a dog. So what we do then is we put the untrained neural network into a deep learning framework. This is a piece of software. You may have heard of examples like Caffe, Torch, Theano, TensorFlow, MXNet, CNTK. There are many of these deep learning frameworks available, and we'll talk about what some of the differences are and how to choose between them in a little bit. But the deep learning framework's fundamental job is to feed these images through the neural network one at a time and to monitor whether the neural network correctly guesses or infers that the image it was shown was a cat or a dog. Now, if the neural network infers correctly that when you show it an image of a cat, it infers that it's a cat, then the job of the deep learning framework is to reinforce the weights, to reinforce the decisions that the neural network made in order to get the correct result. But if the neural network guesses incorrectly, then the job of the neural network is to reduce the contributions or reduce the weights of the perceptrons, the nodes in the neural network that contributed to making the incorrect inference, the incorrect guess. And as you can guess, in the beginning, when the neural network has never seen a picture of a cat or a dog before, it's about 50-50. It doesn't know the difference between a cat and a dog, in the same way that a young human child wouldn't know the difference between a cat and a dog. And in fact, we do see this in young children. Sometimes they'll point to a fuzzy animal and call everything a puppy, even though sometimes it's a cat and sometimes it's a dog and sometimes it's actually a puppy. But over time, as the neural network sees more and more examples and it gets reinforcement when it guesses correctly, and different negative reinforcement, if you will, when it guesses incorrectly, it develops the capability to predict or infer the correct answer much, much more accurately, in many cases more accurately than humans can. And so after you have a trained neural network, you now have something that it's a feature. It's capable of distinguishing between cats and dogs. Now, if you went back and wanted to have a neural network that was able to tell the difference between cats and dogs and raccoons, you would need to first include examples of raccoons in your training data set so that you had examples to teach the neural network. And you would also need to modify that last layer, the bottom layer of the neural network, so that it had 3 output nodes instead of just the 2 for cat and dog. You'd add the third one for the raccoon. So in this trained model, it's now been trained to tell the difference between cats and dogs. And you can see here by the size of the nodes, we're representing the weights that have been tuned or learned into the network specifically for the task of distinguishing between cats and dogs. If we had instead showed this neural network pictures of sedans and pickup trucks, the weights would be very different because the characteristics that those nodes in the neural network would have learned to distinguish between sedans and pickup trucks would have been very different. That's the automation of the feature extraction or the classification rules that we talked about on the previous slide. And now that you have a trained neural network, that's great, but what do you do with it? You now need to put it into some kind of application that is going to go and collect new inputs, new images in this case, that the neural network has never seen, and feed it through the neural network so that you can use it in real life. So for example, as a fun project, one of my colleagues here at NVIDIA has a problem in his front yard where the neighborhood cats like to come and do their business on his yard, on his grass. And that, of course, leaves brown spots, and who wants brown spots on their grass? So he collected thousands of images of cats and dogs from the internet and trained a deep neural network to distinguish the difference between them. And then he hooked up just a USB web camera to his computer. And now when a cat comes onto his yard, the video feed from that camera is understood by the computer. It just looks at kind of one frame at a time. And when it sees a cat, it sends a little signal down a wire to his sprinkler system, and it turns on the sprinklers for 30 seconds or so, just enough to scare the cat off. And his grass is much nicer and has far fewer brown spots now. In fact, he published a step-by-step how-to so that anyone in the world can now very easily duplicate this amazing system at their own home. But all that aside, that same deep neural network, that same network that's been trained to tell the difference between cats and dogs, could be deployed in any kind of application. And to do that, the neural network can be used as is, but if you wanted to optimize the performance of the neural network, there are techniques that you can use to help it to infer new images that it hasn't seen before much faster even than it was able to while it was training. And for that, there's some software called TensorRT that we can talk about in just a moment. So it turns out that deep learning, this approach to automating the understanding of large amounts of data, is stunningly effective across many domains. It's transforming the way computers achieve perceptual tasks, such as pattern recognition, computer vision, speech recognition, and even behavior prediction. As Paul mentioned, some people are referring to this as the fourth industrial revolution after steam, electricity, and the computers and the internet. Some examples you might find interesting is Facebook has a project called Deep Face that looks at many images to create a three-dimensional models of your face from your online photos, and it adjusts for lighting and facial expressions. And then using that model, it's able to identify you in photos with 97% accuracy, all using deep learning. And this is over 27% better than alternative approaches, and on par with the performance of human beings. This is the same feature that Facebook uses to alert you that a picture of you has been posted, which allows you to go in and perhaps blur out the image if it's one that you don't want to be seen in. Another example is Microsoft's Skype translator service, which performs instant translation of conversations in over 40 languages. The killer feature is real-time spoken translation between English and Spanish speakers. A tremendous amount of communication is enabled by this capability. Microsoft servers use deep learning neural networks to transform speech into text, which is then analyzed using standard translation methods. Deep learning is also powerful in many medical use cases. For example, detecting genes associated with the autism spectrum disorder, detecting and suppressing the brainwave patterns responsible for epileptic seizures, and in identifying skin cancers, classifying lung sounds, and computationally designing drugs, saving millions of dollars in research and accelerating the availability of new treatments to patients. Just imagine the day when Facebook can notify you that you might have some skin cancer and you really ought to get that checked out. Other examples in supercomputing include the study of molecular energetics that can lead to breakthroughs in drug discovery and material science. Because trying to do this work on CPU-only systems is extremely time-consuming and very expensive. Here we're seeing work by researchers at the University of Florida and the University of North Carolina, which is leveraging GPU-accelerated deep learning to develop the Ankin-ME solution to reproduce molecular energy surfaces at really, really fast speeds. They're spending just microseconds to do these computations now, to do this analysis, versus what used to take several minutes. Another example is this work by NASA, where they are using satellite imagery to measure the effects of carbon and greenhouse gases on crops and vegetation. They developed a system called DeepSat, which is a deep learning framework for satellite image classification, and trained on their Pleiades GPU-powered supercomputer. The satellite imagery, with this newly enhanced resolution, and now produced at scale, will help scientists to plan and protect our terrestrial ecosystems and help farmers with crop production on our increasingly hotter and drier planet. So let's take a look at some of the challenges that organizations face when adopting deep learning. The first is that because this is a new computing model, there's an increased need for data scientists or people with an understanding of how to apply deep learning to solve these challenging problems. The second is that, as Paul mentioned, the algorithms and the state of the art in deep learning is continuing to evolve rapidly. And keeping up with those new ways of achieving the best results is often a challenge. The third is that training these neural networks, these increasingly complicated and computationally demanding neural networks, requires a tremendous amount of performance to make things that were previously impossible practical and something that we can deploy as products. The fourth is, again, looking at the deployment platforms. Once the neural network is trained, you may need to deploy that in a scale-out data center. You may also want to deploy that in a mobile or an embedded device or in a robot or in a self-driving car. And the ability to take these capabilities embodied in trained neural networks and deploy them on your platform of choice is a challenge for many organizations. So let's look at a few of the things that NVIDIA is doing to help address these challenges. The first is what we call the Deep Learning Institute. The Deep Learning Institute is an initiative that delivers hands-on training for data scientists and software engineers worldwide. In the last 11 months, not quite 11 months, so far this year, the Deep Learning Institute has trained over 7,000 people, delivering over 24,000 hours of hands-on training to help scientists, engineers, and data scientists learn how to apply this amazing new technology to solving challenging problems. The second is the deep learning software that's available from NVIDIA. There are really three different classes of software available to help implement deep learning powered solutions for your organization. The first is a visual interactive tool called NVIDIA Digits. This allows you to organize and manage your data sets, to design and refine your neural network models, to then train neural network models and measure the accuracy and performance of those neural networks against the example data that you feed it, and then provide a trained neural network that is ready for deployment across a variety of applications. The second type of software that is available from many different framework providers are the deep learning frameworks. So these are high-level software frameworks that embody all of the capabilities that you need to take advantage of deep learning. This means that you don't have to learn all of the low-level algorithms and workflow steps in order to take advantage of deep learning. You just need to select a deep learning framework and use that. The good news is that all of the major deep learning frameworks are already up to date with the latest GPU acceleration because they have adopted the NVIDIA Deep Learning SDK. And you have that option as well. If you choose to roll your own or get engaged in deep learning related projects without taking advantage of one of the higher level frameworks, you can choose to build your software on top of the NVIDIA Deep Learning SDK, which provides access to all of the latest algorithms as well as neural network optimization and communication routines. So in addition to the training and the software, organizations also have access to powerful systems for training and deploying neural networks in their data centers and on a variety of platforms. One great example of that is the Dell EMC PowerEdge C4130. This is an integrated deep learning training system that is very powerful for training deep neural networks. You can also choose to take advantage of the Tesla P100 GPUs and the Tesla P40 GPUs in other products. And then once you have your deep neural networks trained in performing the specific task you need them to perform, you can deploy those neural networks into a scale-out data center or an automotive or an embedded application using GPUs that are designed for those platforms. So we talked through some of the challenges and some of the things that NVIDIA that are available from NVIDIA and others to address those challenges. And just to summarize here, so for data scientists and people who need to learn how to apply deep learning to solve challenging problems, there's both the Digits interactive application as well as training courses available from the Deep Learning Institute. To take advantage and keep up with all of the latest algorithms, you can choose to adopt the Deep Learning SDK directly, or you can take advantage of more convenient higher level deep learning frameworks that all include GPU acceleration. For training neural network models, these tremendously computationally intensive training tasks, the PowerEdge C4130 as well as the P100 and P40 GPUs are good choices. And for deployment platforms, you can take advantage of the TensorRT software that I mentioned earlier to help optimize your deep neural networks and choose to deploy those applications on the Tesla P40, P4, or other embedded platforms. So thank you for your time. I hope that you have some interesting challenges and ideas for how to apply this new technology, and that you will choose to take advantage of the GPU-accelerated deep learning frameworks and GPU-accelerated platforms to do your work.
Alrighty, we'll take over now and go into our Q&A discussion. And we have a lot of questions here, so we're going to lead right off with them. And we do have some time, so you can still keep on submitting some questions that we can hopefully get to. I'm going to let either Will or whoever just jump right in here and answer the question as appropriate. We'll ask one here. For language translation learning, what is the learning feedback distinguishing good from bad translation? Anybody?
I can take a shot at that.
Okay.
So there have been many different approaches, and there's actually some great research papers online that go into this in detail. But there are sort of direct approaches that look at individual words, and there are also what I would call more sophisticated approaches that look at phrases. And in most cases, the training data set needs to be labeled ahead of time so that the deep learning framework can supervise the learning process and provide the corrective or supportive feedback to the network as it is trained. That means that you might have a collection of 10,000 words or 100,000 words, the audio recordings of them, and have each of those words be spoken by many different people with maybe slightly different accents, etc. But you would know what the correct answer was for each one of those audio clips in order to effectively train the neural network through reinforcement learning. And you can imagine that same process might be performed in a slightly more sophisticated way by training the neural network based on phrases rather than individual words. It's worth noting that for automated translation, there are really a couple steps. The first is receiving the audio clips and converting them into text. The second is converting the text from one language to another language. And then the third is the text-to-speech, which is translating that back into the language of the person who is wanting to hear it in a different language. And all three of those steps can benefit from deep neural network models. Great question.
Okay. Got another one here in sort of the life science area. How would you apply deep learning in diagnostic pathology? Say, is this tissue normal? Is it benign? Or is it a malignant tumor?
Well, it turns out there's some really compelling work has already been done in this area, both in tumor detection or tumor classification, as well as there's a particular case called diabetic retinopathy, where a number of people with diabetes over the course of their lives develop blindness, and it comes from well, I guess the cause is less important, but we have a medication now. There is medicine that can help prevent or slow down the blindness, diabetic blindness. But it's mostly effective at the very, very early stages of the disease. And so over the years, doctors, optometrists, ophthalmologists have been collecting images of eyes from diabetics, of course, as well as images from non-diabetics. And so we now have this huge big data collection of pictures of people's retinas, some of which eventually turned out to develop this diabetic retinopathy-induced blindness, and some of which did not. And we're able to use those examples to now detect the early onset of the retinopathy, the indications that this blindness is coming on much earlier using deep learning techniques than had previously been possible with human doctors alone. And so this is actually saving people's vision because it's assisting in the early diagnosis of this condition that allows the medicine to then be prescribed and prevent the blindness from becoming serious.
Mm-hmm. Okay. Got another question here. Are there limitations to which types of data I can leverage deep learning today? You talked about text, you talked about images, audio. Are there any limitations to the types of data? Will?
So I'll just take a high-level stab. This is Paul. It can be applied to any data that you have a sufficient body of data to extract patterns from. So we talk about it in security. We talk about it in so many different kinds of contexts. Healthcare data, ambient weather data, anything that can be used to make a decision on. So think about your senses: taste, smell, hearing, sight. It really is a general purpose tool. So I'd say that no, there's not a limitation. The only limitation comes in terms of gathering enough data to feed the models so that the network can train itself to recognize.
Okay. You talked about translation and explained how to go about doing that. And we have a question here. Why can't we do away with the intermediate step of changing audio to text and then back? Do you think much is lost in translation? Do errors get propagated from this intermediate translation step?
This is Will. That's actually a very insightful question because, in fact, there are people who are doing work now. If you wanted to look at some of the research that's been published by Baidu, the large internet services company based in China, they have some really sophisticated models for doing speech recognition and natural language processing. But Google and Microsoft and others have also published some very compelling work in this field. And it is possible to, looking at some of their work, to skip those intermediate steps. It's just a little bit easier to understand when you're coming at deep learning for the first time if I break it down into those constituent steps.
Okay. Switching here a little bit into getting back into the neural nets. How do you determine the required number of layers?
The required number of layers in a neural network? Is that the question? I think I will interpret that as the question then. So there's a little bit of an art and quite a bit of science to determining the optimal neural network topology or design for a particular task. And one of the reasons that many of the examples you see today are based on image classification or object detection or image segmentation, these sort of visual examples, is that much of the early research in applying deep learning and deep neural networks was in these areas, and the neural network models that the researchers used for those were actually published as part of their papers. And in many cases, implementations of those models were made available alongside the deep learning framework software that they published along with their research papers. And so that is definitely one of the kind of easier areas to take advantage of deep learning today. But as larger and larger challenges begin to be tackled by this deep learning technology, the size and complexity, both the number of nodes in a layer and the depth or the number of layers in the network is continuing to increase. And it appears to be the case that to tackle these increasingly complex challenges requires both an increased amount of data in the training set and an increased amount of complexity in the neural network itself to be able to really detect the fine-grained nuance of differences between so many different types of things.
for deep learning, there's for life science, there's a lot of different types of imaging data. There's X-ray data, there's photographic data, there's radiation data. Is there any way that you can compare these different types of data? There's been a problem with regard to not being able to strictly compare one type of data, X-ray data, to image data or anything like that. Is there been some work sort of resolving that?
Well, I'm not aware of any specific examples where it's able to compare X-rays to ultrasounds, for example.
Mm-hmm.
But I could imagine that if you had enough examples of cases where you have patients that had both X-ray and ultrasound data, that you could potentially train a neural network to predict one from the other. I'm not sure if that's what the question is about, but it reminds me of a recent story published by the Children's Hospital in Los Angeles, who has a pediatric intensive care unit, the PICU. And one of their big challenges is that, very young children come into their intensive care unit, usually through the emergency room, with some very serious problems. And they're faced with the challenge of trying to decide which children should get attention first and which children are in the most critical condition, because in many cases the kids can't really speak or clearly communicate what their symptoms are. And what they discovered was that even though they were collecting all of this data, that the best predictor of survival rate for each individual child was whether they survived the first night. And they clearly weren't satisfied with that as a predictor of survival, because they only it was sort of after the fact that they were able to understand whether the child was going to survive the first night. So they looked at these large collections of data. They had all of the admissions records and sensor data from heart rate and blood oxygenation and other mostly non-visual data that they collect on every patient as it comes through their hospital. And they were able to convert much of those different types of data into a sort of single image representing many different inputs across a period of time, and then use those characteristics in the images to train a deep neural network to predict the survival rate for any given patient at the time that they were really first entered the hospital, first entered the care of the hospital. And they believe that this is now dramatically increasing survival rates and quality of care across much of the services they provide. So that's a story that the Children's Hospital in Los Angeles has published, and there's also more details online if you wanted to search for that example.
If I could kind of elaborate on Will's answer, I think that multivariate aspect of what Will just talked about is hugely important. The ability of a neural network in deep learning to take much more varied input than a human can correlate in our minds. Our working memories are, if you're very good, you can hold 15 separate things in your mind at once. Somebody with good working memory. Machines don't have that restriction, and so metadata and different types of data all go into this ability to match a pattern across multiple axes, multiple variables. And that really is the key. It's in the volume of data, and it's also in the types of data that you can cross-correlate, that humans might not even think to cross-correlate. But the pattern, the neural network has access to all of these different types of data and can use it in one pattern recognition activity. Will, is that fair?
Yes, I think that's spot on.
Okay. Got a little bit more of a practical question here. How can existing customers who already have HPC installations take advantage of deep learning today?
Well, that's a great question. I think it really comes down to whether you have GPUs in your existing HPC data center or not. It is possible to train deep neural networks very slowly without GPU accelerators. But in practice, everyone we've come across really is only able to kind of practically start taking advantage of deep learning with the performance provided by GPU accelerators. But we see this in a variety of forms. So often an individual researcher or data scientist will get started by adding a consumer class GPU just to a workstation that they have. And they'll use that for some small scale experimentation using a smaller portion of their data set, understanding that they might not achieve quite the level of accuracy, but as an evaluation, as some initial prototyping. And then once they have sort of organized their data and the neural network model that they believe will work well at scale, they'll deploy that into their data center and use their GPU accelerated HPC systems to train their network on a much larger set of data, or to then explore minor variations in that network design with sort of training it on the same set of data to fully train the network and achieve the levels of accuracy and performance that they need.
And I'll reinforce Will's message with, I've got a hand-built PC running an NVIDIA GTX 1060 card, and I've loaded Baidu's deep learning benchmark suite, and it runs just fine. So you can actually do this on the small scale and scale it all the way up to a distributed cloud environment.
Okay, and we've sort of run out of time here, and I want to thank both of our speakers today, Paul and Will, for their insights and for their responses to our questions. I want to thank our audience for submitting their questions and listening to these very educational type areas. And I want to thank Dell EMC and NVIDIA for their sponsorship of today's webinar. And this will be available on Scientific Computing's website probably within a day or two. For on-demand viewing, you can watch it at 2 o'clock in the morning if you wanted to. So thank you very much for everybody, and have a good day.